Okay, and yeah, it's lovely to see so many people here today. If you want to introduce yourselves and whereabouts in Sussex or wherever you might be in the country, please do go ahead. It's just nice to know where everybody is. My name's Kath Gagan. I help to manage Warmer Sussex along with Natasha Birch, and Natasha's going to be helping me just keep an eye on the chat. So please feel free to use the chat if you've got any questions that come to mind while either of our presenters are speaking this evening. We're going to try and get through as many of those questions as possible at the end. We're going to try and make sure we've got some time at the end to answer some questions, but any questions that we don't get to, we will answer in the next couple of days, and we'll send you all an email with both the presentation and with the questions to any of those answers that we didn't get to. So I just wanted to start by just giving you a brief introduction. For those of you who aren't familiar, Warmer Sussex is a one-stop shop for homeowners across Sussex who want to make their homes warmer, healthier and more energy efficient. We are part of RetrofitWorks, which is a not-for-profit cooperative of energy efficiency experts and local contractors. I'm very pleased to say that tonight we're joined by two experts in the retrofit industry. We've got Alex Hunt from Bright Green Homes. Say hello, Alex.
Hello, everyone.
So Bright Green Homes is a Brighton-based building company that specialises in energy efficiency and is a member of RetrofitWorks. So Alex will be speaking first during our session tonight to talk about the different types of insulation and showing some real-life examples of homes that he has helped to insulate. And then we have Lisa Pasquale. Say hi, Lisa. So Lisa is a technical lead at RetrofitWorks. So she's a building performance expert and technical specialist in low energy design and quality management in construction. And Lisa will be talking about why we need ventilation, explaining the different types of ventilation. So just a reminder that we are recording this session. Please use the chat for asking any questions. And at the end, we'll try and answer as many as we can. Okay, Alex, over to you to get started.
So, hi everyone. Thank you for that, Kath. Yeah, as explained, so I run a firm in Brighton and Hove called Bright Green Homes. We've been going for over 10 years now. I set it up in 2009 with my mum, actually, who's an architect who was very interested in the environmental performance of buildings and improving buildings through energy efficiency. And it was kind of my background as well that got into it. And we've turned into a full service building company, members of the AECB and Trustmark and the Green Register and the Federation of Master Builders. So, I mean, the background to all of this, I'm not going to harp on about this, A, because time's short, and B, because probably most of you know all of this already, and certainly if you don't, the key thing is where we are and where we want to be. And that's, you know, we all know that we've got to reduce our carbon emissions in order to mitigate against the worst effects of climate change that are coming towards us. Texas will tell you all about it at the moment. About 20% of all the buildings, or about 80% of all the buildings in the UK will probably still be with us in 2050. So what we're aiming for is refurbishment. And you'll see from the little graph in the top there, you'll see sort of the little diagram, about a quarter of all the heat that's lost through the building and energy that's lost from your building comes out of the roof. About a third comes through your walls, about a fifth through the windows, 15% through the floors, and drafts and basic pool ventilation, but Lisa will talk a lot about that later on, can also account for the last 15%. I mean, obviously that's averages, so it's not the same in every building, and every building's slightly different, and we live in them slightly differently, and we have them at different temperatures and all that sort of stuff. But it does mean that there's a lot of work to be done. So we've done a fair bit of work in the last decade. They look a little blurry, some of those pictures. But like the building on the top middle there has had cork insulation on the outside with triple glazed windows in the building on the top right. The building in the middle in Steading there has had super insulation and air tightness barriers, and lots of improvements to heating systems, bottom left external wall insulation and solar. Same bottom middle external wall insulation and cladding, new extension, solar PV. Bottom right, external wall insulation, new double glazed windows, all that good stuff. And you know, they're not uninteresting buildings. You know, it doesn't mean that you have to, if you're going to do an eco renovation, it has to be anything uninteresting and box like. If you're going through the process, someone like Warmer Sussex will help you with that first initial measurement and assessment and retrofit assessment and working out what actually needs to be done to the property, because everyone's different and they're all every situation is different and every building is different to some extent. And you know, you really need to know where you start in order to work out where you're going to end up at the end of it all. So this usually goes through a system of then designing it, tweaking that design, talking about how much that design is going to cost, inevitably, more tweaking of the design, and that section in the middle there could go round and round and round for some time. Building work can take time to get right, and it is important that you get it right. And then in the end of it all, then you'll come to potentially someone like myself, who may have been helping with the design section as well, but we will then go through the project management and delivery of the actual work itself to your building. I mean, in an ideal world, all the design tweaking's done and I can walk in and just go, right, we do this, get in, get out, and it's nice and straightforward. Just to give you some of the examples of what can be done, here we added 50 mil of cork insulation, so a really nice natural breathing material to the external walls of a 1950s bungalow, effectively. And then it was externally rendered, and that brought the U value down by about half, effectively. So all the heating that was lost through that building, or certainly the 33% that you would expect to be lost through the walls, is potentially halved in the, you know, in the losses. And here we were doing internal wall insulation for a Victorian terraced house, battening the walls, putting the insulation over what was solid masonry, and then it's replastered, you know, new window boards, new reveals, and genuinely you'd never know that the work had been done once it has been completed. Here was another property where we had some skeelings which were insulated with a PIR insulation, and again battened over with plasterboard. And then in the roof void in that bottom left picture, we put in some earth wall recycled glass insulation into that sort of pitched part of the roof void. You'll see the guys there putting in the solar PV units, and then in another part of the building we had a recycled newspaper called Warm Cell. Lovely in theory, and it is a great product, beautifully recyclable, all those sort of things. Horrible to get out. It's just a real pig. If you ever have to change it, or if there's ever a problem, it's a bit of a pig of a product. But you know, you live and learn. When we're doing loft insulation, we often install what is a raised deck. So here you'll see it is the loft zone system that we recommend. It effectively means that you can continue to have the storage in your roof, but have the foot deep of insulation there. So I'm just going to get one of my guys who is COVIDed up in his mask to tell you all about it.
Loft zone in the loft space. We have laid out the 100 mil insulation in between the rafters, 100 mil insulation, and we are now laying the 200 mil insulation over the top in the opposite direction, in between the loft zone brackets and the steel runners, which will then be covered with the chipboard. Thank you.
And then wait for it. And someone's mobile phone. We haven't specifically put that music over the top of it. It just, you know, but I didn't want to take it out. I thought it added something to it all. And, you know, it is a very straightforward process, actually, insulating lofts, really. It's not a very pleasant job. But there are some things to look out for. You need to make sure that you continue to get ventilation in a cold roof from the eaves, cross ventilation. You don't want condensation forming on the underside of the cold roof, but it can make an enormous difference to your property. And there are all sorts of things to think about. You know, fire safety. If you've got electrical cables in a loft and they are of a certain type of PVC, they don't really like being left underneath much more insulation. They can have a chemical reaction with them. And so you just need to be aware of some of these things. Also making sure that there are eaves vents, or certainly vents in the roof space. What are you going to deal with about your storage? What are you going to do about the loft hatch? Once you've also created the new deck, to put all your storage on, what are you going to do about your original loft ladder? Because obviously now there's a difference in height between the new deck and the floor from whence you arriving. Oh, hang on, skipping too far. So I'll just show you this little one. And then these things, they're called, colloquially, they're known as witches' hats, but they're like fire-rated hats to go over, or protectors to go over the top of LED downlighters. Oh, done it again. Here we go. Sorry. Excuse me. Here we go.
Spotlight insulation witch's hat, which basically goes on the top of the spotlight, so it's not a fire hazard with the insulation. So we're just fitting these now, and then the insulation goes on the top of the witch's hat.
There you go. So you've no idea how difficult it is to persuade the guys to do these little videos. It took hours and hours of cajoling. And then another example of floor insulation here, where we were down on the ground floor. This was actually converting a garage space into a usable home office, which is very pertinent for these days. And this was using PIR insulation or polyisocyanurate. Most people call it by their generic name, Celotex or Recticel, or oh god, what was the other one? Knauf, you know, but PIR is what it actually is. And again, you can make a huge improvement to the heat losses through the floors of your property. Here's an example. Now, we've had some problems with this video, so I might have to show it in a different way. But this is a property we've just done very recently in Brighton, where we're adding earth wall insulation to the underside of a new pine deck floor. It has happened. Okay, just excuse me a sec. Let me get the video up in this way instead. This is one of my other lads, Harry.
So, hang on. Yeah, so Harry's wearing the full PPE, insulated the floor.
Sorry, we can't see that, Alex. You're only sharing the PowerPoint presentation.
Oh, hang on. Right, sorry. Apologies.
No worries.
Nylon netting with staples every 100 mil.
Right, there we go.
Full PPE.
Is that better? See it now?
Cool, yeah, got it.
Floor. The nylon netting with staples every 100 mil. And then just go around all the way on the floor, cutting the floors to insulation, making sure there's a 150 mil gap from the underside of the nylon to the floor beneath, and that there's all ventilation. We're using earth wall, Knauf, mineral wool insulation.
Should get them to sponsor us, really. And it's as complicated and as simple as that. Realistically, most of the work is actually done then in the preparation. Like all of these things, it's 99% in the preparation. So let me just carry on with the presentation. Oh, sorry, excuse me.
Today, so this is.
You can see I'm not a PowerPoint presentation specialist.
Please,
not one of my highlights. Okay, so this is again going back to some of the case studies. As often these are the things that are most interesting for people. It was a coach house in Kemp Town in Brighton. This is one of the properties that we gave a full house, a full home renovation to. You know, it's not an insignificant amount of money, but there was a lot of work done there, and it wasn't, you know, it wasn't just about the energy efficiency. It was also about producing a very beautiful home for a family of 4 eventually. So we did all the plans. I mean, you can see it was looking a bit tired originally, and it was pretty much a sort of student digs sort of quality place, but the opportunity for improvement from a low E on the EPC to a middle B, I guess, showed that there was lots of opportunity to improve the property, which we did. We worked out lots of options of how to do it, and this was kind of the whole house retrofit that I showed you part of earlier on. And again, it was internally insulating the external walls, insulating the roofs, insulating the floors. You know, I could go on about this property for hours and hours, but I'm aware that we have sort of limited time. And again, you know, having done all of this work and put in underfloor heating and put in all the insulation values, you know, some of the most important things were actually nothing about the whiz bang special PV or anything like that. It was just purely how comfortable the house was to live in, that there weren't drafts and you didn't feel cold when you were sat at particular windows. And of course, you know, their energy bills were significantly reduced. So, and their carbon footprint significantly reduced, but that wasn't really the thing that stood out at the end of it, even if it was you know, one of the drivers at the beginning. There's our electrician getting stuck in. He's kind of short, so we put him in the small spaces. And that was the warm cell insulation in the plastic covering there. I mean, it's all loose fill, and yeah, lovely product, but you know, it great in certain circumstances. But again, all through all of, you know, building work, it is a mucky, dirty trade. You know, we create a mess, we're knocking holes in walls, we're managing parking and neighbors, and there was all these sort of things that go with it. So don't expect anyone to just come in and go, aha, we're going to insulate your house, it'll be fine, because it just, you know, it never works like that. And then here we had some examples of what air tightness barriers look like. We were putting in some a mechanical ventilation and heat recovery system to keep the air in the building balanced, but also had the knock-on effect of you can also keep it filtered, which is kind of pertinent at the moment as well. And there we have like the finished article, if you like. So it changed quite significantly, as you can see. I'll never forget that bamboo floor. It cost me a fortune in chop saw blades. But that showed its energy usage across what we did in the various aspects of the overall retrofit. So you can see it drops significantly. And it kind of follows that same graph that we were looking to try and emulate. The one down the bottom there, I think, kind of shows a similar aspect. Another example, again, this is a house of a couple with sort of teenage kids, I guess they were at the time. Again, not insignificant work, but it included the extension and what have you as well. And, you know, it was a fairly standard looking house, you know. We converted the garage and put an extension on the back of the property as well. But again, there was a lot of opportunity for improvement on the EPC as we did it. So we also insulated all of their floors. We worked out what some of the things that we could do to the property would do in terms of its improvement on their EPC rating. You see that in the orange to green. And that then shows what the CO2 output each year would be and what the savings would be. So as we went on through the process, we could kind of had a pretty good idea of what we were going to improve and what that effect would be. So we put solar PV and solar thermal, new heating system, underfloor heating with insulation, air tightness, draft proofing, triple glazed windows. It was what we'd call a deep retrofit. So you can see all of that underfloor heating there and all the lovely insulation in there again.
You're just over 15 minutes, Alex.
Am I already? Blimey.
Yeah.
So there you go. So there's the EWI. And that's just 2 of the case studies. So I really am going to have to fly through this now. There's the new heating system. But we're going to send out copies of these slides, aren't we, Kath? So, you know, if you want to take them at a bit of your own pace. Again, there's putting in some of the air tightness things. But again, this is a deep retrofit. So you wouldn't necessarily do all of these things, certainly not try and stop a skip lorry in the snow, as Simon tried to there, which was always, it's always entertaining to watch anyway, unless you're the boss and worried about insurance. And there was the final aspect of the property. And I think, we'll all say it actually looks very beautiful and is also an eco house that runs really well. Again, following the same path of the various installations, but that again is what we do, a deep retrofit. So I want to quickly say that, those are 80% reductions. That's really what we're trying to aim on any property. But what a lot of Warmer Sussex will be doing is actually some of the first stages of these, like loft insulation, part wall insulation, maybe doing some of the floor. And, these first stage retrofits will get you along the path to where that final deep retrofit might be. And if it's not something you want to do all in one hit, then the idea is to future-proof what you do now so that it doesn't impede what you're going to try and do in the future. And and I'm a big believer in the simple idea that, if you could afford it now, do it. If you can't, just plan for it for when you might be able to in the future. And we don't want to be too militant about it all. And anything you can do to improve the energy efficiency of your house will not only reduce your bills, make it much nicer to live in, but it'll also impact your overall, involvement in our species' increased carbon output. And all we can do for that will help us all in the long run. So I hope that was interesting and some of you found it useful.
Brilliant. Thanks, Alex. That's really, really good.
Stop sharing.
You can stop sharing now.
Yeah. Stop sharing now.
So what we'll do now is move swiftly over to Lisa's presentation. So thanks everybody who's got your questions in the chat, and please do keep adding them. We've got a few interesting ones there that I can't wait to ask, but we'll go through the ventilation stuff first. Right, let me just share my screen. Okay.
Okay.
Yeah.
Okay, great. So let's see. Don't press play quite yet.
YouTube was in control then. Right, off you go.
So hello, my name's Lisa. I'm RetrofitWorks technical lead. So a bit about my background. I'm trained as an architect, but chartered as a building services engineer. And my specialty is in building physics. So basically the way I describe it is I design all the things about building that you can't see, but you feel it, you perceive it, you just, can't exactly knock on wood for it. So the ventilation, lighting, heat, warmth, that's all the stuff that I kind of deal with. I jokingly say that I am the last person that you ever want to lay out a bathroom. I'm rubbish at that. So I'm going to explain a bit why we need to look at ventilation, because this is something that gets quite important when we do retrofits. As we make properties more airtight, better insulated, we fundamentally, especially with older buildings, we change the way that they work in terms of ventilation and how fresh air enters the house, and how we basically extract soil there out of the home, and we change the vapor and the moisture balance of the home, which is very, very important. Now, rather than me go super geeky on you, luckily the UK Centre for Moisture in Buildings has done a really lovely video which explains it in really simple terms. So we're going to show this video, and then I'll explain the different kinds of ventilation systems and how we go about designing them for retrofits.
Okay.
Worried about damp and mould? Don't panic. Help is at hand. First off, we need to understand what the problem is. Damp and mould are caused by an excess of moisture and can create problems for our health and for our buildings. However, just like our bodies, we need some moisture in our houses in order for them to function well. So we need a balanced amount of moisture to keep a healthy home. Moisture can create problems in your home through the many forms water can take. When water freezes, it expands into solid ice, which can burst uninsulated pipework. Liquid water from leaks or flooding can lead to damp in the floors or walls. If your guttering becomes blocked, then rainwater can overflow, saturating your walls in specific areas, sometimes even leaking through to the inside. But the most important form we want to discuss here is water as a gas, water vapour. Whilst we're all used to the sight of steam from a boiling kettle, most water vapour is not so easy to spot. There is always water vapour in the air around us. We produce it when we breathe, along with any animals or plants in our home, and also through daily activities such as cooking and washing. If there was no water vapour in the air, then nothing would be able to live. Okay, so here's the technical bit. In different temperatures, air can hold different amounts of water vapour. The warmer the air is, the more moisture it can hold, known as its holding capacity. But when there is more water vapour than can be held by the air, it becomes full up and condenses into liquid water. Outside of your home, this is how rain is formed. This also happens when warm, moisture-rich air meets a cold surface, like a single glazed window in your home during winter. Condensation forms as the air suddenly cools against the surface and the holding capacity of the air is reduced. Because air can hold different amounts of moisture at different temperatures, we measure how full the air is by something called relative humidity. If we have 100% relative humidity, then the air is full up and the vapour becomes liquid water. But even when there is no condensation, high relative humidity can be uncomfortable and lead to mould and other problems. At the other end of the scale, air with 0% relative humidity is excessively, and in fact, impossibly dry and uninhabitable. We need a relative humidity of somewhere between 40% and 65% for most of the time for the building atmosphere to be pleasant and healthy. So we come back to balance. Not too dry, not too moist. Where does the moisture in your house come from? Outside of the home, the most obvious answer is rain. Good construction is vital to avoid water entering a building from the roof, walls and windows, along with suitable ground drainage in the case of flooding. Inside, we have our direct uses of water in our daily lives, washing and drying clothes, cooking and bathing. All these produce visible liquid water and large amounts of not so visible water vapour. Next, we have the organisms within the home, human, animal and plant. All of us produce water vapour as we breathe, or plant breathe. If the number of people, pets or plants changes, the balance of moisture within your home may change dramatically. Remember how hot and humid the air gets at busy parties. But you didn't have a problem before. What's changed? For damp and mould to appear in your home, you need an excess of moisture, visible or not, that leads to an imbalance. What has changed? Has something stopped working? Has the weather changed? Or have you changed the way you live? Or have you made improvements to your home? Home improvements need attention to detail, and sometimes they can put things out of balance. For example, improving windows or insulation is great for heat retention, but if the installation leaves gaps, it can create colder areas called cold bridges, where the moisture can condense and mould can grow. If you draft-proof your home but ventilation is not also considered, then moisture levels can rise and push the house out of balance. So a good ventilation strategy is needed. Different types of building in different locations need different approaches in order to maintain balance. Older buildings deal with moisture in a different way to newer ones, so require a different approach when renovations or changes are made. Buildings in windy, wet places often have different kinds of materials and design. If we don't take these into account when we change things, we can end up creating more problems. What to do about it? There's a lot to think about, but the key is to hold on to the idea of balance, the balance between the water, outside and in, your house, and your activities. Firstly, understand your building and how it was designed to work and stay healthy. And try to understand the building as a whole, fabric, services, occupants, and its context, as all these factors are connected. Try to stop any excess water getting into your home, from the roof, windows, walls, or foundations, and also the internal plumbing. Check for leaks, missing tiles on the roof, broken seals around windows, and cracks in the render. This is obvious, but not always straightforward. Simple maintenance is always a good starting point. Try to reduce the excess moisture from your activities within the home, for example, by keeping lids on pans or drying clothes outside. This is not always easy in winter or if you have limited space, but do what you can. Finally, make sure the water vapour generated in your home stays at a healthy level through proper heating to increase the holding capacity in the air, and good ventilation to get rid of excess vapour. Try to understand your home's ventilation system if it has one. This can mean opening windows when you know an excess of vapour is being created. It's easier to heat your house if it's well insulated, of course, but remember that a consistent approach should be taken so that you don't have an imbalance of warm and cold surfaces. One more thing. Don't worry about little bits of damp or mould, particularly around windows or in showers and bathrooms. It's quite normal, especially in extreme weather conditions. Sometimes there is not much you can do except wipe the water or mould away. Just keep an eye on things and ask an expert if you're not sure. To learn more about the causes of damp and the balance of actions, check out our tool here. Living in a balanced home is good for the health of the building, its occupants, and their wallets.
Right. So, am I on mute? No, okay. So the reason that we need ventilation is ultimately to maintain this balance of moisture within the home. So like the video said, is as you insulate your home, you make it a bit more airtight, you make it easier to contain the heat. That heat has greater holding capacity of moisture, which means if you're not regularly changing the air over, that moisture can build up over time and start to create a problem. So effectively, to prevent that buildup of moisture over time, we want to make sure that we give purpose-provided ventilation for a home to make sure that the air changes are adequate to both remove the moisture, but also to remove smells, keep dust mites and stuff like that under control. And nowadays, very, very importantly, to take viruses, bacteria and whatnot out of the air as well. So it is quite important to continuously ventilate a home. So with traditional construction, like older buildings, ventilation was typically provided by the fact that the house was just really leaky. So there were drafts coming in everywhere, which meant that there was a constant changeover of air. So that was kind of, fine back in the day, but obviously it's not a very efficient way of handling things when we've got central heating now. So we're putting a lot of heat into the homes. The last thing we want is that heat to go spilling out into the outside environment. So as we work to contain that heat, we then need to provide active ventilation. So the way that we design it is based on a number of different attributes within a home. So we look at the number of occupants or bed spaces, whichever is largest, to basically size how many people and how much water vapor that the ventilation system is going to have to accommodate. We look at the number of wet rooms, including baths, kitchens, toilets, utility rooms, drawing rooms, anything like that. We look at the ability for air to travel between rooms, because ultimately what we want to do is extract the moist air out of the house, which usually means extract fans in all of those wet rooms. But in order to do that effectively, we need to be drawing air from the habitable rooms, like the bedrooms, the living rooms, halls. So usually that happens with using undercuts to doors. So a little gap underneath the door, which allows the air to move from one room to another. We want to look to make sure that we've got a clean, safe, adequately sized intake. So in some cases, that'll be trickle vents in the windows. In some cases, you have specialized air vents in the actual wall itself. We want to make sure that we have adequately sized extract from the wet rooms to remove moistures and smells. And this is sized based on the various attributes, the size of the home and how it's used. We look to make sure that if we do have ducting in the home, so basically metal tubes that pull the air from one location to another, that we've minimized how far those duct runs are to get the air either into the home or back out, whichever way we've designed it. And that's quite important because the longer the duct run is, the bigger the fan is that you need to push the air. So the more energy that it actually demands to move the air through that duct. We always want to employ demand control, which is basically humidity sensing. So the older kind of vents that you see in bathrooms often are tripped off by the light. So you turn the light on in the bathroom, the fan kicks on, it'll stay on until you shut the light off, and then it might, you know, continue on for 10 or 15 minutes after you've shut the bathroom light off. And similarly with kitchen extracts, you turn it on when you're cooking, you turn it back off. We're trying to move away from that and turn towards humidity sensing, so that rather than needing to actively control it, it will sense that actually something's happened in that room that means it needs to boost back up. So that's a way of using intelligent controls to maintain the efficiency of the system. We want to recover heat from the extracted air when it's feasible, because obviously if we're making a house more energy efficient, we don't want to be pulling all the heat directly out the ventilation and chucking it to the cold air if we don't have to. So we want to look at how we can recover heat and recycle it back into the intake air to kind of reduce how much energy the ventilation is using. Next slide. So the different types of ventilation that we look to employ, and this depends a bit what type of system we use, depending on what level the building is at in terms of its air tightness and what other attributes are going on. So the most common one that you'll probably be familiar with is what we call intermittent extract ventilation. So that's effectively just fans in the bathroom, kitchen, wet rooms that kick on now and again, either based on when you activate them, whether they're hooked onto a light sensor, but basically, according to the regs now, we need to have them humidistat controlled. But these are only actually feasible in relatively leaky homes. So if we're doing a deep retrofit, usually we'll push the envelope of the building beyond the point where intermittent extract ventilation will provide a balanced internal environment. So we have to be a bit cautious about relying on this as a strategy now. So it's only feasible in relatively leaky homes, and it relies partially on background ventilation being provided by uncontrolled drafts. But it also relies on trickle vents within the home, which is usually in windows and other locations. So the extract fans are in the wet rooms. They only operate when they're required. So they shut off completely once they sense they're no longer needed. And the cross ventilation between the rooms again is via undercuts for the doors. So like I said, this is quite common with houses at the moment. You'll probably have, you know, bathroom fans or kitchen fans that have this kind of style. But as we kind of go towards improving building performance and improving the retrofit of domestic houses, we have to kind of move away from the strategy a bit. So the next slide. Passive stack ventilation. So this is one that's is a bit difficult to retrofit, but you might have it in an existing home, especially if it's kind of a 70s, 80s era home. It's only, again, feasible with relatively leaky homes. It does rely partially on background ventilation being provided by uncontrolled drafts. And again, extracts from all the wet rooms, but these are ducted up to the roof ridge of the house. And it relies on a pressure differential between the top of the roof and the rest of the house to suck air out of the home. So effectively, it's a bit like blowing across the top of a bottle and creating a bit of a sort of suction, which creates a hum on the bottle. If any of you guys did that when you were kids. So effectively, this kind of passive stack pulls the air out. But again, it's not something that's easy to retrofit because we do have to run ducts up through the house and then change the ridge line to provide that extract. Intakes again are through trickle vents in the windows in all the rooms, and that includes the wet rooms. But again, you can use through wall vents from some specialist companies. Next slide. So as we
just at 15 minutes, Lisa.
Oh, dear, that was fast. Video is longer than I realized. So mechanical extract ventilation. So this is a bit more common for what we do at retrofits. So this is only feasible when we have relatively good levels of airtightness of a house. So we aim for, in techie terms, 5 cubic meters of air movement per meter square of envelope area at 50 Pascal, which is basically the test that we use to gauge air tightness. There are extract fans in the rep rooms which operate 24/7. So they're always on a very low level. And then they boost when they sense the humidity rise. And that boost lasts until the humidity comes back down. So effectively, they only boost up to a high level when they're required. And that helps make them much more energy efficient. They can be either centralized or decentralized, which means you can either have fans that go directly out the walls in the bathroom and the kitchens, or you can have ducts from the wet rooms coming to a central fan box, which then go out the house in one location. Next one. And mechanical ventilation with heat recovery. That's the last slide. So this is only feasible with very good levels of air tightness. So you need to have less than 3 cubic meters at 50 Pascal for air changes, which is quite a good level. It's a very similar principle to mechanical extract ventilation in that it is extracting again out the wet rooms 24/7 at low level. It boosts when it's required. You could also boost it if you just want it. So if you're in the kitchen and it's getting a bit smelly, you can hit the boost button and give it a bit more air. However, there's a single point of intake instead of relying on trickle vents around the house. And that's the main difference with this system, is you can't use trickle vents with it. The single point of intake then indirectly exchanges the heat with the extract air. And what that means is the intake air and the extract air don't mix. They go past each other with a heat exchanger in between. So effectively, the warm air comes into the house at a kind of tepid level of kind of 12-15 degrees. And it goes out the house at a much cooler level than it otherwise would normally come in. So if you've got a cold winter day where it's 2 degrees outside, rather than having a 2-degree draft coming in through the window through a trickle vent, you've got warm air coming in through ducts in the house into the habitable rooms, which is more at about 12 degrees. So it's much more comfortable. You're recovering a lot of the heat that you would otherwise be taking out of the ventilation system. It's always centralized, so there's a single kind of big fan box with an intake and an extract relatively near each other, but not that close. But the one trick with it is the ducts do require quite a bit of space. So it is tricky to install, it's tricky to design, and it needs a lot of thought in how it goes into an existing building. And a really, really important point is that there's heat exchangers and especially the filters, because MVHR has filtered in incoming air. They need regular maintenance. So you need to be changing them regularly, otherwise they get quite nasty. But again, this is the system that provides the cleanest and the most efficient form of ventilation. And if we look at the post-COVID world, this is the system that is going to be the most hygienic in terms of not risking recycled air coming back into the house. So, right, I think that's all from me.
Excellent. Thank you very much, Lisa. So now we've got a bit of time for some Q&A, and I know there's been a few questions asked in the group already. I'm actually going to stop sharing so I can have a look at all the questions. And I'll ask either Alex or Lisa to decide who feels best equipped to answer these questions. Right, the first one is from Anis. So saying, okay, talking about scare stories about cavity wall insulation. So please explain, is it safe? I guess that depends, doesn't it? Who wants to answer that one?
Go for it.
Go for that. We can both do that one.
Yeah.
So I'll start with that. So cavity wall, it can be safe when it's done properly. So a really important point, especially with you guys down in Sussex, is that cavity wall insulation should never be installed in areas that are very exposed to wind-driven rain. And that's largely where installs have failed. So Wales being, in particular, being quite vulnerable. And likewise, I live up in Glasgow. You can't install cavity wall in most of Scotland. We just get absolutely pelted with rain and it's just not feasible. If you're in a relatively sheltered or moderate wind-driven rain area where you're unlikely to get your house absolutely pummeled with driving rain, it's much safer. It again then depends on the type of insulation that goes into that cavity. So there are certain types which are more robust than others. And again, it depends a bit on the actual construction of the building as to what's appropriate. So I would say it can be done. It cannot be done in every case. It cannot be done on every cavity. And it cannot be done with any material. They do all have to be kind of matched together. And that goes back to Alex's point about, context, the existing construction and making sure that the strategy is all tied up properly. Alex, do you want to add anything?
Well, I was just going to say, I mean, locally in Brighton and Hove, we have always specified ourselves that we go with an eco bead, which is graphite covered and is installed with like a PVA solution. So effectively it becomes like a plastic layer within that cavity, which stops water penetrating from the external leaf of masonry to the internal leaf of masonry. The problem that's often been that's happened in the past is that they've used either blown fiber or mineral fibers, which are effectively glass fibers, and they create a channel for the water to move from one leaf to the next. Whereas the beads, it's like filling a bean bag effectively, but it's they're blown in with a PVA solution, and it does create a waterproof layer. I mean, it works brilliantly well in the right circumstances. There's no disruption, can all be done from outside. As long as nobody's left big holes in the inside of your house, you shouldn't have lots of polystyrene balls flowing into your living room while it's happening or anything like that. Although we have seen that in the past. And I would recommend anyone, if you are thinking about doing a cavity wall, is to get a reputable SEGA registered installer to come and have a look, potentially take a boroscope in and have a look in the cavities and see if they're partially filled or whether there's lots of snots, lots of bits of masonry that's going to prevent any of the polystyrene beads from spreading in an even way. Get a proper registered guy to do it. Don't go for the cheapest option, which is unfortunately very common in all of the construction business, is that the better the product, it's going to cost you a bit more.
Yeah, so it is very important to choose the right product, because PU foam is another one that can be used, which can improve the water tightness of the home. But yeah, it's also important to make sure, especially with getting reputable installers, that they make sure that the cavity is fully clear, because some of the fails that we've seen were from people that just basically kind of did a drive-by, drilled a couple holes, squirted some insulation in. And we looked at it with kind of thermal imaging cameras, and you could see just spotty insulation where they filled that bit and then they filled that bit over there and that bit over there, and it didn't all join up. And the poor guy inside the house has, like they showed in the video, just strips of mold where all those cold spots are. So it is about making sure that the job is done right by someone who knows what they're doing, and knows how to specify and install the correct product.
Brilliant. Thank you both. The next question from Stefan was, I'd like to know how to get independent advice about the best ways to make our home better insulated. Is it worth getting an EPC energy performance certificate? Stefan should have been on our webinar last week because we covered this. But you can listen back. It's on our website. So Warmer Sussex offers independent advice. We have retrofit coordinators who will survey your home and take a view of all the improvements that you could make to it, and will come up with a series of recommendations based on a conversation with you. So they don't work for us at Warmer Sussex. They're members of our cooperative. So we feel that their advice is, the right advice for you in your home. But please do look at our webinar from last week, because we go into a little bit more detail about that advice. And there, as well as Warmer Sussex, there's also BESCO, Brighton Hove Energy Service Cooperative. So particularly in the Brighton area, if that's where you are, they also offer energy advice surveys. And as you saw at the beginning, Alex also can, you can speak to Alex afterwards. I'm sure he'll give you a reasonable quote for that kind of advice as well, and the kind of help that he can give you.
I mean, there are a number as well of very well qualified people that have been working in this business for a long time, who could probably help you with that. I would suggest, obviously there's Warmer Sussex and BESCO, but also there's the members of the Association of Environmentally Conscious Building, or they call it the Sustainable Building Association these days. And there are members of the Passive House Trust, and they may push you towards a passive house end solution, which may not be appropriate for your property, but there are lots of people around, and there are some architects as well who have specialized in the energy efficiency side of things for a long time. But yeah, I mean, I think again it comes back to using an accredited registered person who clearly has the right qualifications and understanding of doing it. We
definitely go into that in a bit more detail, so have a look at that on our website. So the next question from Andy Arnold. Hello, Andy. It'd be useful to understand the risks and mitigation measures available to avoid damp issues from improving insulation. Who wants to tackle that one? Risk and mitigation issues, measures available to avoid damp issues, other than specifying really well.
So, the main risks are around underventilation and thermal bridging. Those are two of the main ones. So basically, cold bridges and thermal bridges, we want to make sure that the internal surfaces of the house are as consistent as possible. So what we don't want is a house that's sitting at about 21 degrees with most of the surfaces sitting at about 19 degrees, and then a bit around the window which is sitting at 10 degrees, because that's where you get that mold and condensation issue. So what we try and focus on is making sure that the insulation is as continuous as possible all the way around the envelope. The areas around window reveals, doors, at the base plinth level of the floor, as well as up around the eave level of the roof, are all well insulated, and all that insulation is well joined up. So if we do that, that should mitigate a lot of the risk of spot condensation and mold within a home. And like we said, is if there are issues like that that are already there because someone previously has done something, usually we can go back and find a way to remedy it. So we have seen a number of homes where cowboys have gone in, 8-10 years ago, done something, and we've got to go back and redo it and figure out a way to kind of resolve the surface temperatures to take that risk away. So yeah, that and ventilation are the two kind of key things.
The next question is similar. This is from Nick Owen, saying if there are voids in the cavity wall insulation and the aim is to put external wall insulation on the outside, do the voids matter? Should I get it all taken out and refill with beads?
Depends. Is the answer.
Depends. You need consult an expert.
Consult an expert. I would say yes, in an ideal world, you should have the faulty cavity wall insulation removed first. But having said that, if you're going to put on a quite significant layer of external wall insulation, which brings the dew point of the wall further out into that section, then it doesn't matter what you've got in the cavity. It just might be that it doesn't work as well as if that cavity was fully filled. But, I mean, again, it depends. If that cavity is very poorly filled and only half the wall, or there's spots everywhere, I mean, unfortunately, there's no just simple, straightforward answer. Otherwise, I'd be out of work.
Yeah, so I'd agree with that, as it does just depend a bit on the conditions of the home. It also depends whether or not damp, what material is in there, and if damp has already gotten in. Because obviously if it is kind of a wool type material and it's soaking damp, for one reason or another, you do kind of want to get it out of there. So yeah, it just depends on the conditions of the house, but it's worth kind of having someone go out and have a look.
Okay, and the next question from Heather. She's asking, is acoustic insulation denser? Does it have thermal properties? If providing wall insulation but soundproofing is also a goal, can it provide effect for insulating too?
So yeah, effectively, there's quite a number of insulations that will provide both. So most insulations will also have, thermal insulations will also have an acoustic buffering effect, some a bit more than others. So yeah, they could always kind of be effectively joined up, so that you get both an acoustic kind of soundproofing or sound mitigation, but also kind of a thermal envelope improvement as well. And maybe Alex can suggest some types of insulations.
I don't know if I get the specific manufacturers, but I mean, what Cami said is that sound insulation is all about changing densities.
Mm-hmm.
So if you've got multiple layers of different densities in any element, whether it's a window or a wall, it's going to improve the sound deadening properties of it. So you know, one of the flip sides, or not flip sides, one of the unintended consequences of triple glazed windows is often people go, blimey, I can't hear the traffic anymore. You know, or with insulation between floors in houses, you know, you're not hearing the people running around upstairs as much. And you'd be surprised how many properties simply have, you know, a wooden deck joist with a void and then a plasterboard ceiling, and you know, and then they wonder why it's so noisy upstairs. So you know, yeah, yes is the answer, and yes, there are multiple different products out there. We've done it for lots of party walls of various different densities of material on top of one another, and you know, and it does offer insulating values as well.
Okay, brilliant. So next question from Ruth. Oh, I think that we can do that. So she's asking, she says, thanks, Alex. Can we get an indication of what the EPCs of some of the case studies ended up at, please? So if we can,
well, yeah, well, we always try and
pass those on if you've got that.
With the deep retrofit, I mean, we're looking for an 80% improvement, really. So effectively, we'd be looking to get to the final. Oh, hang on, let me see if I can get you the right. Where I showed those graphs before, I think. There we go. It's just now. How do I share the screen again? There we go. Share screen. There we go. So that one there. I mean, effectively, you're bringing it down so that these would then become a high B rating. I mean, if you can get a property even better than that, I mean, this is where a graph like this, and actually what Warmer Sussex can offer in amongst their online tool that you can find on the website. But these are the kind of calculations that RetrofitWorks and Bright Green Homes have been doing using the SAP software, which is the standard assessment procedure for the energy efficiency of dwellings, which doesn't roll off the tongue, so that's why everyone calls it SAP. And it effectively shows you where it started at a SAP rating of 43, which is a sort of low E, or low E. And then by each of those interventions, adding a new boiler, what that reduces the extra insulation in the floor. And you'll see this kind of law of diminishing returns. So the nearer you get to an 80% improvement, the harder those final improvements are to reach. New boilers will make a huge difference. If your existing boiler is 10, 15 years old, you get yourself a new gas condensing one, you're going to save about a third of your energy bills straight away, you know, with something that's pretty straightforward. But yeah, I mean, when we do work, we always try and aim for the AB rating. I mean, actually, an A rating in a old house, it would be pretty impressive by anyone's imagination. So I think, you know, if you, like I say, if you are planning a renovation on your own property, you really want to start looking for the 60%, 70% improvement. If you get yourself to a decent C, maybe low B rating, I think you're doing extremely well on an existing property. I hope that answers your question.
Thanks, Alex. Okay. All right, question on ventilation. We'll just do a couple of these. I know we're a little bit over time, but I think we just want to cover a couple of the ventilation ones, and then we can go back on the answer the rest of them. Let's have a look. So, is it possible to measure your relative humidity yourself? Says
Yes.
Rebecca.
Yeah, so quite simply, actually, you can go get little temperature and relative humidity monitor sensors. I mean, you can get them off Amazon for about a tenner, and they just give a little digital readout for what it is in the house. It won't save the day or anything fancy like that, but it'll give you an instantaneous number, so you can kind of get in a sense of, you know, after you get out the shower, what it's hit. You know, after you've made a pot of pasta in the kitchen, what it's sitting at. And like the video said, is we aim for about 40 to 65% most of the time. Obviously, sometimes when you're cooking or you've had a shower, it'll bump up to about 80%, but we want to see that kind of come back down relatively quickly.
Cool. And a question from Toby's asking, what's your opinion on window vents versus active ventilation?
So I'm assuming with window vents, you mean kind of keeping windows cracked open. Well, that's something that requires you to actually kind of open or close it. So effectively, we're a bit hesitant to use those sorts of things just because if we use ventilation where you have to open something, it relies on someone consciously kind of doing something. And the main thing that we want to do with active ventilation is make sure that it's just it's running in the background, that you're constantly being supplied with fresh air. Because to be quite honest, your brain really isn't programmed to send you an alert to say, oh no, it's too humid in my house, I must open a window. By the time that's happened, it's been sitting at that level for quite a long time. So what we want to do is have an active ventilation system which is constantly supplying fresh air and healthy air, so that you're not really having to think about it or doing anything active. It's also a bit of a security thing as well. You don't want to be leaving windows cracked open, ideally when you're sleeping. So if you've got a ventilation system which is running in the background, which basically someone can't jimmy open with a wrecking bar, that's kind of a better scenario, I think. I live in a ground floor flat in Glasgow. It's always a concern. So.
Okay, I'm just going to skip through just a couple of other ventilation questions because we've had quite a few of the insulation ones. There's an interesting one here from Ruth Martin saying, what happens with MVHR when the outside air is very moist, which it often is in this country?
So when the air is very moist, because it's very cold, like they said, the relative humidity and the absolute amount of moisture it's holding, even when it's absolutely completely saturated. So right now in Glasgow, it's absolutely chucking it down, has been all day because it's Glasgow. But it's only about 6 degrees outside. Inside, it's 21 degrees. It's nice and warm. So effectively, as that moist air is being drawn in from the MVHR, compared to the amount of moisture that can be held by air at 21 degrees, there's actually relatively little absolute moisture in that air, believe it or not. So even though it's completely saturated, because it's cold, it doesn't actually hold that much moisture. So as it goes through the MVHR and the heat is exchanged and it warms up, that's actually much drier air that's being brought in. And that's the whole nature of the dew point of how much air it can actually hold at a given temperature. So that's why MVHR is actually quite efficient, and it doesn't bring as much dampness into the home as you might expect.
Okay, brilliant. So I'll do one more question and then we'll wrap up because we're a little bit over. So there's a question here from Neil Murphy about positive input ventilation units without heat recovery. Any thoughts? Do they work okay in older properties?
So positive input ventilation is quite a specialist ventilation strategy. It can work. There are certain scenarios where we would use it. It's not something that we jump to specify when we've insulated a property in certain ways. And it's just because when we positively pressurize a house, it means instead of cold drafts coming in, we've got warm drafts going out. And when we've got warm drafts going out, if they're creeping into parts of the building which are quite cold, so the outsides of walls or potentially internal elements of the building like joist ends and stuff like that, if those elements of the building are cold and that warm moist air goes in, it can condense in those areas and then potentially cause a problem in a relatively invisible area of the house where you won't know that mold and rot's starting to take holds until it's a bit late. So that's why we're a bit hesitant to use it. There are certain scenarios where we will use it, sometimes in high radon areas. So it is a one way of mitigating some radon risk. There's also certain types of insulation that are much lower risk to use that with than others. So again, it's just about having a balanced approach. It's not about the age of the building as to whether it works or not. It's really about the insulation strategy and the context of the building as to whether or not we'd be comfortable putting it in.
Brilliant.
Okay.
Thank you, Lisa. So I'm going to wrap it up there. So thank you everybody who's joined tonight. And of course, thank you very much to Alex and to Lisa for your expertise and sharing that with us freely. As I said at the beginning, we will answer all the questions that you've popped into the chat here. We'll send an email out to everybody with the recording of this. And we'll also post it onto our Warmer Sussex website, so warmersussex.co.uk, and that's where you will see the recording of last week's webinar. We're hoping to schedule a webinar pretty soon with another one of our members of our cooperative on renewable heating and solar PV. Haven't got a date yet, but if you follow either our website, you can sign up to our newsletter or keep an eye on our Eventbrite page and you'll see it when it comes up and you can sign up to that. So thank you very much, everybody, for joining us this evening.
Thank you all.
Thanks.
Take care. Bye-bye for now.
Cheers. Bye-bye.